In this next set of videos, and we'll split this into 2 videos so that we can fully accomplish both parts, we're going to be talking about the surface area and volume of hexagonal prisms. So let's start by reviewing the vocabulary associated with them. A hexagonal prism is a prism whose bases are hexagons. Specifically, we are finding the surface area and volume of hexagonal prisms whose bases are regular hexagons. This means the hexagon is equilateral and has 6 congruent sides, and equiangular has 6 congruent angles. The height of the prism is the perpendicular distance between the bases. So as we already know, the bases of a hexagonal prism are these hexagons, and the distance between the bases is what we call the height. The height, as always, will still be determined, or referred to rather, as h. All right, now let's talk about some kind of background information. Regular polygons, as we've already seen with squares, for example, and the equilateral triangles, have what is called the apothem. The apothem, as we've said before, is a segment extending from the center of the polygon, where the diagonals intersect, to the midpoint of one of its sides. And we'll look at that apothem here in this example in just a little bit. But in terms of a regular hexagon, another thing that's true about a regular hexagon that is not true of other regular polygons is that it can be divided up into a series of 6 equilateral triangles by drawing in the diagonals. So as we start to draw the diagonals in this particular instance, we'll start to see these equilateral triangles develop. The other thing that we know to be true, since these are equilateral triangles, not only are the 3 sides of each triangle congruent to each other, but because the polygon is a regular polygon to begin with, all 6 of these triangles will be congruent, which means if I'm trying to find the area of the hexagon, then it's just as easy to find the area of one of these triangles and multiply it by 6. Likewise, if I can find the length of the side of one of the triangles, finding the perimeter of the hexagon would be quite easy. Now, in terms of the apothem, we said the apothem extends from the center of the polygon to the midpoint of one of its sides. In this case, if I draw the apothem here, label it A, we can see that the apothem forms the height of the equilateral triangle that we're trying to find the area of, which in turn helps us find the area and perimeter of the hexagon itself. So in terms of the hexagons, the approach we'll be taking is to find the area of one of the triangles and then multiply that by 6 to find the area of the base. All right, so let's practice that with a couple of examples. And in these 2 examples, we have a different value, or the value given is in a different position. In this position, it's what we refer to as the radius. We call it the radius because it's possible to draw a circle centered at the center of the polygon that would pass through each of the vertices. In this case, we know that if we were to, using the example up here above, if we were to draw another radius from the center to a vertex, that those would have to be congruent segments because this triangle has to be an equilateral triangle, which tells us if that side is 14 units long, then this side is 14 units long, and this edge of the polygon is 14 units long. Right away, I now have the ability to determine the perimeter of this hexagon. We know one side length is 14 units long, so the perimeter of the whole thing would be 14 times 6, or 84 units for the perimeter of that polygon. Now let's deal with the area. To find the area of the triangle, and then multiply it by 6, but to find the area of the triangle, we start by drawing its height in. When you draw in the height in an equilateral triangle, it divides the opposite side into 2 congruent parts. So this side that was 14 units long is now split into 2 parts, each 7 units long. But consider for a moment this right triangle on the right side. It has a hypotenuse of 14 and one leg 7 units long, which is half of 14. You should recognize this as a 30, 60, 90 triangle. where the short leg is half of the hypotenuse, and where the longer leg is found by taking the shorter leg's length times the square root of 3. So this distance for the apothem will be 7 square root 3. Now let's deal with finding the area of the triangle. We have the base, the entire base of this triangle. Remember, we're finding the area of the equilateral triangle. So the area of that equilateral triangle has 14 as its base and 7 square root 3 as its height. So for the area of the triangle, we take 1/2 base times height, 1/2 of 14 times the height, 7 square root 3. And since this isn't our final answer, it's not the entire area, I'm not going to put that into a calculator because that square root of 3 is going to be an irrational number that's never going to end or repeat. So for that reason, we'll deal just with these other real or rational number components out here at the front, these coefficients. 1/2 times 14 times 7. So 1/2 times 14 is 7. 7 times 7 is 49. So the area of the triangle would be 49 square root 3. Now let's deal with that or use that to help us determine the area of the hexagon. We've already said that the hexagon, this regular hexagon, is composed of 6 equilateral triangles. If this is the area of one of the equilateral triangles, then the entire area of that base would be 6 for the 6 triangles times 49 root 3, the area of each one of the triangles. Now, if you're asked for an exact answer, then you'd simply want to take 6 times 49. Don't include the square root 3 because there again it's going to give you that irrational result that we don't want. 294, which is 6 times 49, square root 3, units squared for our area. If we were looking for a decimal version, then I'd go ahead and type that into the calculator. Now in terms of surface area and volume, those are determined by the area of the base, the perimeter of the base, and the height of the solid. So for that reason, when I'm finding surface area and volume, this will not be my end result, which means I don't want to make that a rounded decimal answer at this stage. I only want to round the surface area and volume themselves. All right, let's look at another example where we are not given the length. Here we were given the length from the center to the vertex. In this case, that is not the case. I don't have it properly marked here, but this is to be the midpoint of a side, and that's to be a right angle. So in this case, what we're given is the apothem. And we're going to start it in much the same way by drawing in the 2 radii. We want to create one of those equilateral triangles. We don't know the lengths of any of the sides of the triangle, of this equilateral triangle, but if I can find the length of one side, then I know the length of all 3. Okay, so with the apothem, the 30, 60, 90 relationship, the apothem is the long leg. Now with our 30, 60, 90 relationships, we said that the length of the shorter leg times root 3 would equal the length of the longer leg. In this case, our longer leg is 5 units long. Our shorter leg in that right triangle is here as half of the side. Let's call that x for the time being. So in this case, x is the short leg times the square root of 3 must equal 5. We need to solve that for x. So we divide both sides by the square root of 3. And rationalize what we have on the right side, multiplying both the numerator and denominator by the square root of 3. So 5 square root 3 over 3. In this case, the 5 is not evenly divisible by 3, so we'll leave that as the length of x. Remember, x is the length of half of the side. So if this is 5 root 3 over 3, and that one is the same length, then the length of the entire side, take this up here, the side length of the polygon would be 2 times 5 square root 3 over 3. And when it comes to multiplying by 2, think of that 2 as 2 over 1, and we'll multiply appropriately. Don't make it a 2 over 2. Okay, so we multiply across. 5 times 2 gives us 10 square root 3. Remember, the root 3 is unaffected because it's only the two whole numbers get multiplied together, but the radical stays the way it is. And in the denominator, we're left with a 3. Here again, 10 is not evenly divisible by that whole number 3, so we'll leave it in that form. And that's the length of our side. Once you have the length of the side, you can do just as we did up above, find the length of the perimeter, and then use it to find the area of the triangle, which in turn will give you the area of the base. All right, so let's deal with our perimeter. The perimeter is 6 side lengths, so 6 times 10 root 3 over 3. Now when we multiply, in this case, 6 over 1, again, remember those whole numbers. 6 times 10 gives us 60 square root 3. 1 times 3 gives us 3. But this time we can simplify. 60 is divisible by 3. So for that reason, we will go ahead and divide. 60 divided by 3 is 20 square root 3 units. Now when it comes to finding the area of the polygon, the area of the hexagon in this case, we want to start by finding the area of one of the equilateral triangles. So for the area of the triangle itself, we would take 1/2 times the side of the entire equilateral. Remember that side length was 10 square root 3 over 3. Times the height of the triangle, which was the apothem 5. Think of that 5 as 5 over 1 if necessary. So in the numerator, we're going to multiply together what we have. 5 times 10 times 1 is 50 square root 3. In the denominator, 2 times 3 times 1 is 6. Reduce 50 over 6, and the area becomes 25 square root 3 over 3. And that's the area of one triangle. So the area of the base, B, is made up of 6 of those triangles. Think of that 6 as 6 over 1. Now, you can either multiply straight across. 6 times 25 is 150 root 3. 1 times 3 gives us 3. You could also reduce at this stage instead of multiplying first. So I could take the 3 into the 6 twice and then multiply across. Now, in this case, what you're doing is dividing both the 6 and the 3 by 3. 6 divided by 3 is 2. 3 divided by 3 leaves a 1 in this position. So in our denominator, we have 1 times 1, which is 1. In the numerator, though, 2 times 25 gives us 50 square root 3 units squared. And that becomes the area of the base. So in the case of an equilateral triangle, finding its area, finding its perimeter can be, as it appears here, quite lengthy. Leaves a lot of opportunity for mistakes to be made, so you have to be cautious when doing these. Analyze and organize your work. The more organized you can make it, the easier it will be if you do make a mistake to go back and find it. Also, if you have a question and you're talking to either myself or another student about a mistake that maybe you can't locate in your work, having it organized is going to make that process easier. So to simplify your trouble with any of these, try to be methodical in your solution process. Okay, in the next video we'll talk about actually how to use this then to find the surface area and the volume of a hexagonal prism.